Hello, everybody. So we've got a neat topic in this video. We're generally talking about volume and how we can use integrals, which we have so far seen as useful for areas, to get volumes. And also, one thing I want us to recognize is, besides this specific application, we're seeing a technique. So the technique we used to find integrals, right? We had a complicated area, a complicated shape. We approximated it with something simple, or maybe another way to say it is we had a shape whose height was constantly changing, and we approximated it with shapes whose heights was constant, our rectangles, and then added them all up for an approximation, and then shrunk our intervals until the approximation gets closer and closer, and we got all this limit stuff, right? But this idea of approximating something that's changing, the height of our function, with a series of things that's constant is a technique we can apply in a lot of places besides area. We're going to see it here applied to the idea of volume, but it's a way more general technique that can be applied in lots of different places, right? Things like pressure, or from physics you can do work, you could do it with profit, you could do it with lots and lots of different contexts, okay? Changing temperatures, all these kinds of things. So let's apply it to volume, and we're going to start by looking at volumes of what we would call cylinders, okay? So we typically think of a cylinder, this shape here on the left, this is a circular cylinder. So we have these two faces that are circles, right? And then it's like the shape has been extruded, like those clay games or little molds that kids have. You can press clay out right in a single shape. So you've got kind of there's some definition. You could draw a straight line through the points in each of these faces. It's all the lines that hit, I think, at a 90-degree angle. That might be a sufficient definition, but we don't need a perfect definition. We just need the idea of a cylinder. And if you want the area of this thing, the volume of this cylinder, you start with the area of one of the faces. They're the same, and you need the height, right? And then the volume is just that area times the height, right? In this case, the area of one of the faces is pi times the radius times the height. Over here, let's call the area of this height of this triangle A, got a height here. So this volume is A times H. Here, the area of the triangle would be 1/2 the base times the height of the triangle, then times the height of the cylinder, right? But in both cases, we took the area of the face of the cylinder and multiplied it by the height. And that it doesn't matter what the shape is, right? If I try to make some weird shape, as long as the shape's the same on the top and the bottom, if we can figure out the area of this face, we can multiply it by the height, right? So this is like a general idea. However, what happens if the area is not changing? So for instance, the area is not the same on the top and the bottom. It is changing. So suppose I have something, there's my shape, but as we move along, so I'm organizing it horizontally now, right? The shape changes, right? So the area over here, maybe on this side, if we could see through this thing, it just turned into kind of a square shape, right? It's got some little curves in here and all this kind of stuff. The area is changing along this entire thing, right? And if I slice it at any point, so for instance, suppose I sliced it right here, I might get some, right, depending on how this thing is changing, right? It's some different area than both of these, for instance, okay? So the area is changing everywhere along the way. So now we can use that technique of approximating something that's changing with things that are constant, and then using that approximation to approximate the whole thing. So let me explain a little more clearly. What I could do is, so starting at this face on the left edge, let's pretend we have a cylinder with exactly the same area at each place, right? The shape is actually changing a little bit, but I'm pretending it's perfectly cylindrical for this first interval. And then I go to the next place and I do that again. It's got some different shape, right? If I can make a cylinder out of this shape in the middle. There's cylinders over here that are different shapes. And so each of these cylinders approximates the volume of the shape near it. Let's look at a much, much, much better drawing than mine. This is a difficult thing to draw. Huh. Well, let me grab it for some reason. Let's see. Ah, there we go. All right. So let's look mostly at the right two shapes here. All right. Oh, I thought I could cover up that thing, but so look at what we're looking at here. This blue shape here is what is the kind of thing we're trying to approximate, right? Its area is changing all the way through. So what we do is approximate it with this stack of cylinders we see here, right? So each cylinder, notice each cylinder has the same area all the way through. If you sliced each of these cylinders, in this case, they're all circles, but of changing size. But each one, in and of itself, has a single area for its entire height or width because they're on its side, right? And so it's this idea of each of these is now, let's say this is a collection of cylinders. Right? Versus here, and I'll just say it as an ever-changing cross-sectional, I don't think that's right, but I'm going to leave it, area. Meaning, if I slice this thing, right, if I took a knife and sliced it vertically, at each place I slice it, there's a different area. And we're approximating it with this collection of cylinders, okay? So then the idea will be that's our approximate volume, and if we make those cylinders smaller and smaller and smaller, then we can get a better approximation. All right, let's try to do this. So let's organize a little bit more. I'll try to do a simpler drawing to make things a little bit easier, I hope, to see. So here's the idea. Suppose we have a solid that's not a right cylinder. So I'm going to draw something not too complicated, I hope. Okay. We're going to arrange it above the x-axis. Putting in an axis here, okay. All right, because this will let us name something. So I'm just sort of imagining this thing floating above the x-axis somewhere, okay? Now, let's mark the endpoints. Let's say it goes from A to B, okay? All right. Now, if I imagine slicing this, if I pick a point in this interval, let's call it x sub I, right? And I slice this shape, it's going to have some area. If I sliced it somewhere else, there would be a different area, right? So I'm imagining a three-dimensional object and slicing it vertically, right? So imagine the shape. If you had an apple and you sliced an apple in half, you can imagine these kind of like two lobes of the apple. That's the shape. And if you sliced it near the edge, you get something maybe closer to a circle, but much smaller. Okay, so depending on where you slice it, you get different shapes. This is what I mean by the cross-sectional area. At each place, there's a different area. Okay, so what we're going to do, we're going to divide our interval up into n intervals. So we have our large interval from A to V. We're going to divide into n intervals, right? X1, X2, X3, and so on. I'm just picking an arbitrary one in the middle that I'm calling Xi. Okay. The area at each Xi, the cross-sectional area, I'm going to write this way. A of Xi equals the cross-sectional area. Okay. Notice it's a function. Depending on which of these we pick, we get a different area. You input which place you're slicing it at, you'll get a different area popping out. Okay. So what we're going to do now, remember our slabs from these approximating discs or slabs, this collection of cylinders we looked at above. I'm going to pretend that the area at Xi remains constant over this whole interval, right? So you can see in my drawing that the actual volume looks like it maybe moves in a little bit. The shape is narrowing after we pass where I drew it, but I'm pretending it stays constant there, okay? Well, we'll call the width, as usual, delta x. So this shape, this red shape that I have, has its width is the same, delta x, and the area of the face is AXI. Right? That's the area of this cross-sectional area of this slab that we chose. Okay? That means the volume of the ith slab, the volume of this piece that I'm drawing, is equal to the area times the height of that slab. But what's the height of that slab? It's on its side, so it's the width. But in either case, it's delta x. That gives us the approximate volume of this shape over this interval. Okay. Now, what about the volume of the entire shape? Well, we can, sorry, that looks bad. I don't know why. Did something weird there. We can approximate the volume of the entire shape. If we do this process for each of these slabs and add them up, right? I'm not going to try to draw it completely, but imagine if I continued this process, slicing at each place, making a little slab. There's a little slab here. There'd be another one here. It's pretty hard to draw, right? This drawing up above, this much nicer drawing up above, is the idea. We get an approximation to the actual shape. And so I'm adding up for each of these x values. There's an area. And then that area represents, that area will take to be the area of the slab over that interval, even though the actual shape is changing. Okay. Now, you can see there's problems, right? If you look closely at this drawing, there's a little gap in there. My original here is getting a little overestimation. And the way we can fix this is the same way we fix it in integrals. Make our intervals smaller, right? We make our intervals smaller. And then we'll get a better approximation. You make them smaller, you get a better approximation. So making the intervals smaller is equivalent to making the number of slabs, remember n was the number of slabs we were using, we make that bigger, right? If we divide this up into more little intervals, we're going to have a smaller interval, right? So we just keep dividing up into more and more. And so we'll take the limit as n goes to infinity of this expression. But we know what happens in this limit. This is a familiar kind of a limit. We've been doing this, that's been this whole series of videos. This becomes the volume from a to b is going to be the integral from a to b of the function a of x dx. Okay? And that's how we'll define the volume of shapes like this. Okay? Right? This is precisely the definition of the integral for the function a of x. Okay? Finding a of x is going to be the tricky part of these problems. Right? We're given a shape, we need to figure out what the volume, or sorry, the area is at each slice, right? In my drawing, it's not kind of a regular shape. So we're going to mostly see things like changing circles, like we saw up here. This diagram in the upper right, or squares or triangles, things we know how to find the area of. Okay, let's do an example that might help clarify this. All right, this is definitely a tricky concept. So here's an image, a graph. We're going to do a function here. Move this up a little bit. Oops. Oh, it won't let me go down then. Okay, in any event, we're going to take, so the way we're going to create our object that we're going to find the volume of is we're going to imagine rotating a graph around a line. Okay, so we're going to, let me make the problem statement. We're going to imagine rotate the graph of y equals the square root of x around the x-axis from 0 to 4. Okay? And we're going to find the volume of the object described above. Okay, so this might be a little hard to picture. Let's see what we can do here. So here I have the graph of square root of x from 0 to 4. What we want to do is rotate this graph around the x-axis. So the x-axis is in red here. And as I slide this, there's a rotation happening. It might be hard to see. We'll change our angle in a second. So now let's do that rotation again. So now our graph, we're looking at it at an angle. If I rotate that graph around, I create this shape, right? It's like a bowl. And the volume we want is the volume that would fit in that bowl. That's the volume we're talking about. Okay? So that's the idea. Now, what we need, so let me write our formula down. The volume is going to be the integral from 0 to 4, a of x dx. And our job right now is to find a of x. Okay? So what we have to imagine is if I were to slice oops, I guess I can't draw on top of it. If I were to slice this object, so maybe I'll do my own little sketch of it to make it easier. If I were to slice this object, okay, so whoops, oh, I know what's happening. All right, sorry about that. Let me draw it down here. Here's my graph I've rotated it around to create a shape like this. Okay, maybe I'll put in the axis up there. Let's make it a little thicker and move it to the middle. So there's my shape. What I need to find is if I were to pick a point on this axis, an x value, and slice the shape at that, what's the area of the shape that I get? Okay, that's what our a of x function is. Okay, it's one that tells us the area for each value of x when we make a slice. Okay, so let's figure this out. The area, I usually do it this way. I think as a single slice. If I pick an x sub I, what's the area of this slice? Well, I know it's a circle, right? Because I've done this rotation. So it's pi times the radius squared. Okay. Well, looking at my picture, what's the radius? The radius is determined by the function, right? The reason this circle doesn't go up much higher is because it stops when it hits the function, right? At any point, it's that distance. What is this distance? Well, this is a point on the graph of y equals, so here's my point x sub I, y sub I, that's the point on the graph. The y value is the height. So the y coordinate at each point is the height. But what we know is that because this is the function square root of x, the y value is just the square root of whatever the x value is. So if I pick an x value, I know the height to the function there is the square root of that value. For instance, if I chose, let's say this was x equals 1, the height should be y equals 1 because the square root of 1 is 1. If I went out to x equals 4, the height should be 2 because the square root of 4 is 2, right? So at each point along here, the height, how high up the function is the square root of the value of x that we've chosen, which means, and that height is the radius, so the area of the ith rectangle or ith circle is pi times the square root of x sub I squared, or pi times x sub I. Okay, so that turns out to be pretty simple. So that means we can now generalize this for any x value. The area for any x value is just going to be pi times x, right? So if I pick any x value along this axis, and I want to know the area of the circle, if I sliced it there, all I do is multiply it by pi, okay? And so now this gives me the formula I was looking for. My volume is the integral from 0 to 4, a of x, which I now know to be pi x dx. This integral is relatively straightforward. We'll get pi over 2 x squared evaluated from 0 to 4, which is going to give me pi over 2 times 16 minus 0, or 8 pi. Okay? And that is the volume of the shape that we were looking at. Okay? So the tricky part of these kinds of things, this is our first example. It was pretty straightforward to find the volume, but with some practice that can all be done relatively easy. We are going to complicate things. We'll stop this one here, but I'll just give you a little preview of some of the things we might do. even just looking at this function being rotated, I can also decide not to rotate it around the x-axis. For instance, what if instead of around the x-axis, I rotated it around that line a little bit above the graph? Well, now when I rotate it around, I get a very different shape, right? Figuring out the radius there will be a whole different trick. We'll work on that. Or perhaps I rotate it around where it's in the middle of the graph, so it does a much stranger kind of shape, right? So there'll be a few things we can do with these that complicate things, but they all have the same basic idea. We have to find the area function, right? Something that gives me the area of the slice at each place, okay? So we'll do some more examples in other videos. That will be it for now. This is the basic idea. And then we'll complicate things as we move forward. All right, thanks everybody. See you next time.